Hello and welcome back. So let's talk about Rolle's theorem. Now Rolle's is very similar to MVT. Rolle's theorem simply states that if we have a differentiable function that has the same y values at two different x values. So in other words, I'm at x equals a here and I'm at x equals b here. If we have a differentiable function, which means it's going to be smooth, right? It's going to be smooth. Then at some point in between, the slope has to be 0. And that's what it says. It makes sense. If you throw something straight up in the air, it comes back and it lands in the exact same spot or near to it. At some point, we have to turn around. That's what Rolle's theorem says. At some point, you're turning around. If you start and end at the same place, you're turning around. If you start at home, you go to school, you go home. At some point, your direction had to change. We can guarantee that because our slope would be, at some point, the slope has to be 0. Now, there has to be some conditions, of course. One, the function must be continuous on a to b and differentiable, again, on the open interval. Again, this looks just like MVT right here. But there is one caveat, there's one little difference. At this time, we just say the value at the beginning and the value at the end have to be the same. Then if the value at the end and the value at the end, beginning and the end, have to be the same, then we say there's at least one number such that the derivative of our function has to equal 0. In other words, that the instantaneous rate of change is 0. Remember, 0, that's my average rate of change right there. Because remember, this is just going to be, if I were to do this, f of a, if I were to bring the b over minus f of b, I would get 0. So that's really the whole hallmark of Rolle's theorem, that if I were to subtract my y values, I would get 0. Now again, do you need to really use this? No, not always. It does have its applications, which we will talk about, but this is becoming bigger in the AP lately, and that we want that slope to become 0, or that we can guarantee a slope of 0. So let's see how we use it. It's very easy to use. Show that the conditions of Rolle's theorem are met. And then find C again, that the Rolle's theorem guarantees. So again, this is going to be find where does the derivative equal 0 this time. So it's really easy to do. The first thing we're going to do is I want to test Rolle's theorem. So I am going to check my endpoints. To find the value at, oops, let me do it the other way. There we go. I'm going to find the value at -2. And if I did that, that's going to give me 4 plus 2 minus 6, which is 0. And I'm going to check the value at 3. Plug in 3, 9 minus 3 minus 6, again is 0. So that checks out. So my one condition checks out, that the values are the same. So this is a differentiable and continuous function. So therefore, at some point, the slope is 0. So we can say, well, since this condition checks out, f of x, and we're going to say it is a continuous, is continuous on the closed domain 2 to 3 and differentiable on the open interval negative 2 to 3. Therefore, Rolle's holds, or Rolle's applies, just like MVT applies, and somewhere on that domain, negative 2 to 3, that the slope, the derivative, has to be 0. So there it is. There's our answer. Next, now we just have to show it. Ready? Find where. Where does that occur? Where. So now we're saying that the derivative has to be 0. That's all we have to do. So we take the derivative, 2x minus 1. You might be thinking, yo, Mr. Warnow, this sounds kind of like a critical number. That's right. Rolle's guarantees critical numbers. Did you hear that? I'm upside down. Rolle's guarantees critical numbers for us. And because it guarantees critical numbers, it's very useful. So here we can say x equals 1/2. And just check your domain. Check the domain, make sure it works. It does. 1/2 is between -2 and 3. You're like, Mr. Warnow says find C. Okay. Therefore, C equals 1/2. All right. Happy now? All right. Let's get tricky with it. For the next one, we want to see if Rolle's applies. So I'm going to check it. Find f of 0. Well, sine of 0 is just 0. f of 2 pi. If I plug in the pi, I get sine of 2 pi, which is also 0. They are the same, which is what I want, and then I can use my rule. F of x is continuous on the closed interval, negative 2 to 3, and differentiable on the open interval, negative 2 to 3. Therefore, Rolle's holds, just sounds fun to say that, applies, and somewhere on that interval, negative 2 to 3, the derivative has to be 0. There it is. Now we just got to find where that occurs. Okay, this is going to get tricky with it. Where does f prime of x equal 0? So we're going to set our derivative, our instantaneous rate of change, our IROC equals 0. So, ready? Taking the derivative of sine, we get cosine of 2x, chain rule, times 2 equals 0. I don't worry about the 2, it just goes away. And we saw the other day, we took the derivative of 2x, and we had to find out where does cosine equal 0, pi over 2, 3 pi over 2, but remember, this is going around the circle twice. So we got to double it. So we go 5 pi over 2, 7 pi over 2, and then I divide by 2. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. But when you check your domain, remember my domain is from 0 to pi. My domain, I don't need the last two. They're too big. So we only pick the first two. And there's our answer. Easy peasy. All right. Real world example. All right, here we go. So this is a really kind of question we tend to see on the AP a lot nowadays. It's popping up. And not just in the AP, but in life in general. Ready? Bilbo, well, not necessarily Bilbo. Bilbo started riding his horse at 12 p.m. He rode for 4 hours straight. And during that time, he traveled 60 miles. We want to explain why there must be a time during those 4 hours his speed was exactly 15 miles per hour. So we are trying to find out. So they are telling us that the instantaneous rate of change is 15 miles per hour. Anytime they mention instantaneous rate of change, we need to think mean value theorem. That's going to be the big hint that we're going to be using the mean value theorem on these type of questions right here. So let's see what they're going to be doing here. Let's see what we're going to be doing here. All right, so mean value theorem. Well, if I find the average rate of change, I can find Bilbo's average rate of change pretty easily. The average rate of change, that's just like my velocity equation right there. Change in distance over change in time. Well, the distance was 60 miles, and he traveled that in 4 hours. 60 over 4 is just 15 miles per hour. So we take a look. Well, his average rate of change is 15 miles per hour. That means at some point his speedometer on his horse also had to read 15 miles per hour. That is brilliant. So we can now say that if your speedometer if your average was 15 miles per hour, to get that average, at some point you had to be above it, and at some point you had to be below it. So if you're going from below 15 to above 15, at some time you have to be 15. That's the intermediate value theorem. So we can use that to our advantage here. So we're going to say that the time is definitely continuous. So we will say f of x with a function of the riding, I guess, is continuous on those 4 hours, continuous during those 4 hours. I guess, let me see here. During those 4 hours. And differentiable as well. Therefore, because the average rate of change was 15 miles per hour, at some point, at some time, Bilbo's instantaneous rate of change was 15 miles per hour. And now comes the most important part. By the mean value theorem. There we go. That's it. Piece of cake. You're going to see this one on the homework, on a quiz, perhaps a test. You want to see that one. All right, the last one. Let f be a function that is differentiable on 1 to 10. Now, if they're saying differentiable, we know it's going to be continuous. Okay? We've talked about that before. Differentiability implies continuity. They're telling us that the value at 2 is equal to negative 5, and the value at 9 is equal to negative 5. Which of the following is true? Must be true. So I'm going to kind of sketch it out. At 2, my value is at negative 5. And at 9, my value is at negative 5. So if I were to look at this, must we cross the x-axis? If I were to connect these two, I want to connect them. That's what I want to do. If I were to connect these, must it cross the x-axis? And of course the answer is no. The graph has at least one horizontal tangent. Ah, well, we know what that means. A horizontal tangent, that's where the slope is 0. That sounds awfully like Rolle's, a lot like Rolle's theorem. And if we know this, we have the same values. I am starting and ending at the same value. That is Rolle's theorem. They're the same. So that one has to be true for us. All right, I hope you guys have enjoyed the video. I will see you all later. Bye-bye.